So maybe, yeah, I think we should get started, maybe, right? I mean, otherwise we'll get very late in the night. That's the thing.
Yeah.
Okay, so I think I am okay with it, and also
Okay,
now
okay,
it's for you to take care of.
great. Yeah, it's my pleasure to welcome my colleague and Professor Sadiq Rangwala of the Ram Research Institute to deliver the first talk of this session.
Hi, should I start?
No. So, Professor Rangwala did his PhD at the Tata Institute of Fundamental Research, Mumbai, where he studied electron dissociation and association dynamics in molecular systems. Thereafter, he entered the then emerging field of laser cooling of atoms by doing postdoctoral tenures at Institute of Optics, Orsay, France, and at the Max Planck Institute of Quantum Optics, Garching, Germany. He has been a faculty at the Ram Research Institute, Bangalore from 2004 and has been doing very interesting studies of sympathetic cooling of ions by neutral atom, amongst other things. Sadiq today will tell us about his work on symmetry, collision, exchange, and diffusion in ultracold ion-atom collisions. Let me now request Professor Rangwala to deliver his talk. He has expressed his wish to take longish questions at the end of his talk, whereas short questions which will help you understand what's happening subsequently can be taken in between. Sadiq, please go ahead.
Right. So thank you very much. I would like to start by really thanking the organizers for putting up such a fantastic program. I mean, it is really a tour de force to get the speaker list that you have so far. And I mean, I look forward to the conference. So without further ado, let me go to the topic of today's talk. And the basic, so the work I will report on today is essentially done in collaboration with these people. Niranjan and Nishant are mainstays of a lot of the work which is done. Amarendra has been doing a lot of the calculations on which it's the spinal cord of this work, and Olivier and Robin are colleagues who we have been talking the science out with quite in detail. Okay, so so I'm going to take a rather broad sweep, and I'm going to give you a kind of a story which kind of puts together 10 years of work and gives it a perspective. So let me start by basically, I will start with telling you what hybrid traps experiments are very briefly and introduce the experimental platform that we are using. Then I will talk to you about what is the origin of the exchange symmetry that we intend to exploit throughout our work, and what is the effect on ion-atom collisions that the exchange symmetry has, the link between the cross sections and diffusion, the collision cross section and diffusion that emerges, what is charge hopping, and then I will go and tell you what is really extremely exciting for the future in this domain. And these are some of the pieces of work. The ones in blue are yet to appear in the public domain, but they will come out very shortly, definitely on the archive soon. So, so basically, we have been doing hybrid trap experiments with ions and atoms. And what is the system? Let's just first, we want to know that if you put a single ion in a cloud of atoms, which are all very cold, what is the consequence of this? How does the system evolve? And this is kind of, it's a bit exploratory because there are certain things that we do not actually understand with these kind of things, and it can be fairly hard to compute, as you will figure out as I go along. So essentially, in our case, okay, when you divide this class of, you can divide this class of experiments in many ways, but one way we choose to divide it is that ion and the atom are different species, and ion and the atom are the same species. And here I'm going to tell you what are the consequences of the ion and atom being the same species, and how does that impact the physics. So homonuclear systems are going to be talked about. These have an additional symmetry compared to heteronuclear systems. And here we will explore the consequences of this thing, sorry. So the basic interaction that we are talking about is the ion-atom interaction, which is a 1 by r power 4. Is my video on? Am I visible?
Your video is not visible, Sadiq.
Yeah, because my camera is switched off.
I see. Okay.
Just a second. This is very annoying. Keeps happening once in a while. So let me try and continue here. And so I'm sorry, but the videos doesn't seem to. Okay, I will try and fix it a little bit later. Maybe somebody will pause it.
Lenovo laptop?
Sorry?
Is it a Lenovo laptop?
No, it's an Asus laptop.
You might just have a F function which got pressed accidentally.
Yeah, but I don't want to end up worse than I am right now.
Okay.
Okay, so start my video. Okay, yeah. Okay, so I think my video is back. Oh, fantastic. So Andal, you can prompt me, please. This came from the host. Okay, so here is how a hybrid ion atom trap works. In the school, Stefan Willich talked about it in quite a lot of detail. And so this is our version of the hybrid ion trap, where you have in a vacuum system, you have 2 cavity mirrors. And you can control the spacing between these. You have optical trap beams, light beams. You have charge particle detectors, and in the central core you have wires and electrodes which create a Paul trap. You can do multiple different kinds of Paul trap. Then you can make a magneto-optical trap right at the center, and around that there is a volume in which the ions are also captured. So you can essentially, in this particular conception of the hybrid trap experiment, we can trap combinations of ions, atoms, molecules, and light in the same experiment, and we can choose which interaction between which 2 species we want to do. So that's about. So now let me go on to the motivation of why we are doing it. So in the school, the students, people have been talking about laser cooling of ions and atoms. In our case, when we are putting the ions and atoms together, and the laser cooling of ions is a pretty challenging issue. And when we are putting these, there are many steps, and you go to the ground state of the ion trap. But in our situation, we are not talking about ions which can be laser cooled. We are talking about alkali atoms which have been ionized to form an alkali ion. And there is a utility for this. And one of the things that is really emergent, and Stefan Willich has talked much about this, which is essentially that if you trap a bunch of ions in an ion trap and you see how fast they eliminate from the trap just because of heating, because you have made the trap in a certain way and that heats the ions. Now, if in addition to the ions, you put a cold gas of atoms, it will sympathetically cool with the ions, and this is the ions will sympathetically cool with the atoms. And here you can see that the lifetime is extended, which means that of the ions in the trap is extended, which means that the ions are being cooled. The blue diamonds are for rubidium atoms cooling cesium ions. And now the red ones is cesium atoms cooling cesium ions. And you can see that the cooling of cesium ions with cesium atoms is much, much, much better. And that signals something. If you look at it from a theory perspective, the cooling of cesium atoms by rubidium, cesium ions by rubidium atoms with elastic collisions should have been more efficient than cesium ions with cesium atoms. So, given the fact that this gap emerged, is indicative of a symmetry. This work has actually, this data is due to Sourav, who is one of the organizers of this school, and it has been observed first in our group in 2012. Actually 2010, it took about 2 years to publish this. Okay, so what is happening? So this signal, the fact that cesium was so effectively cooling an ion, the cesium ion was being so effectively cooled, signaled that there was a new mechanism at play. And that mechanism was a resonant charge exchange process, which means that if you have an atom which is sitting at the center of the atom trap, and you have a fast ion which is coming in and making a glancing collision, there is a split second of time when these two brush past each other, where the electron on the atom can hop to the ion, because these are homonuclear. All the physics that I'm going to discuss is for homonuclear systems. There is no energy cost for the electron to hop, and you can have a fast atom move out and a cold ion at the center of the atom and ion trap. And this is something that Sourav has measured and a long time ago, I mean a couple of years ago. And essentially what is happening here is this is an ion which is coming in. So let me reverse it again. A fast ion is coming in. As it passes the atom, it picks up the electron, and that picking up is at roughly a probability of half. Okay, and a fast atom goes out, and a cold ion stays trapped. So this was cooling by resonant charge exchange. Now, we always were ever since we started seeing these signals, we were very enthused by the possibility of exploiting the symmetry. And what I'm going to talk about now is, in some sense, the exploitation of the symmetry in our in the rest of the stuff. So now we want to take this class of experiment to ultra cold temperatures. Okay, and our motivations are to actually do an experiment which allows us to study these consequences of this symmetry. So now you have to make a selection. We were at very high mass, rubidium, cesium, and even potassium. However, as you have figured out in the school, it is very difficult to make a very low temperature ion. It's far easier to cool atoms to lower temperatures, but the ions keep jiggling around, and even in the ground state, etc. I mean, there is it's the ultimate temperature to which you take an atom in an atom trap and the ion in the ion trap is quite different. So essentially what you want to do is, if you want to go to the quantum regime, you want to move the temperature of the atom up so that it is at a place where you can cool the ions, and you can then study the consequences of the interaction between ions and atoms. Given this particular situation, how do you do that? As you increase the mass of as you decrease the mass of the atom, it basically goes to quantum degeneracy, etc. at higher temperatures, and so lithium becomes the obvious choice for doing these experiments. So that's how we determine that we want to study a lithium ion atom system. And so in order to study this, first you have to know what the system actually is. So first you do a calculation to get the molecular potential energy curves of the lithium system. These are the ground and first excited state of the lithium ion atom pair. And so you have the ground state and the first excited state, the G and the U symmetry, and the calculation is a fairly involved many body ab initio calculation, which has been done by Amrendra. Right. Now you can do this part where the perturbation is large between the G and the U quite well using these techniques, but then you have to match it to the asymptotic form. And there you essentially have certain asymptotic form which are basically representative of the interaction and the exchange part of the potential. And you have to put all these things together and determine the full potential energy curve. Okay, so now we have the full potential energy curve, and what happens? So now you want to know what is the exchange part of this potential in the system. And the exchange part in the system is the difference between the Vg and the Vu, the G and the U curve. The difference in that gives you the exchange energy. Okay, and that's the figure on the right. Just a second. That's this figure. Right. Now, the point is that the atom-ion collisions are happening on this particular potential, right? On this system. So an atom and ion are coming together from asymptotic domain. And so the G and U are the terms, the states which are asymptotically degenerate. Okay. So at large separations, you do not know whether this thing is in the G or the U state, and these are equally probable. So now let's imagine what's happening. Let's say for a moment that you had a heteronuclear system. So the ion and the atom were different and distinguishable species. Okay. And now they collide. So now you have the thing where you get a forward elastic scattering, okay, of the ion and the atom. And you get a backward elastic scattering of the ion and atoms. Remember, we are in the ground states. There is no internal excitation that we are postulating. Everything, the energies are so low that there's no internal excitation that's being postulated. However, now if you allow for the symmetry, now if you make it homonuclear, then you have to allow for forward elastic scattering with charge exchange and backward elastic scattering with charge exchange. So two more possible scenarios have opened up. And because these two possible scenarios have opened up, you get the total differential cross section has to be written in form of G state, okay, at theta pi minus theta, U state pi, theta pi minus theta, and then the converse with the symmetry flip, because if you have bosons or fermions, this makes a difference. So the total cross section, okay, is basically the integral of this over the entire solid angle. And so what are the amplitudes which you have to put in? The amplitudes are in terms of your Legendre polynomial and phase shifts, and that's how the amplitudes look. And the total cross section in this particular scenario is given by this expression, where you are seeing essentially it's the addition of these amplitudes with even and odd indices with x and 1 minus x here, and the x will be determined by the spin of the nuclear spin, okay, in the homonuclear system. So this is the expression which is to be used for cross-section computation. Now, so what you find when you look at literature, cross-sections are very often, in fact, the large majority of the cases in which cross-sections are reported, they are erroneously reported, because what happens is that for a homonuclear system, the direct elastic collision and the resonant charge exchange cross-sections are treated separately. They give you a graph like what you're seeing on the screen for elastic scattering and for charge exchange scattering. And this is not right for homonuclear system. At higher energies, and there are reasons for why this has happened, but at higher energies, you can, if you wish, make this separation, but at low energies, you cannot. And since we are in this regime where we have to do the quantum problem properly, we are in the low regime, and it becomes important, and the cross sections indeed shift. This shift may not look much, but like much, but you have to remember this is a log scale, so it's a factor of 25% and so on and so forth. So it is a substantial shift that you can observe, and you can do this for lithium-6, you can do this for lithium-7, and you can get the cross sections. There is only one cross section, which is the total cross section, and everything is subsumed in the total cross section. So now let's look at diffusion. Now you have diffusion. So let's imagine that you have an ion, which is in a cloud of atoms, and this ion has some energy, and it is going to drift away. It's going to go through uniform rectilinear motion through this cloud of ions. Okay. Now, if there is interaction with the atoms, sorry, cloud of atoms. Okay, there's a single ion in a cloud of atoms. So if there is an interaction between the atoms and the ion, then what is diffusion? Diffusion is the measure of deviation of the ion's trajectory from its ballistic trajectory if there were no interactions. Okay, so this is what the diffusion is. And it is also called the momentum transfer. Okay, this is the momentum transfer cross section. As it is measured, it's a measure of the forward momentum that has been lost by the ion. And if you look at the diffusion cross section, this is how the diffusion cross section is written. And at the lowest energies, where there is only S-wave collisions, and S-wave collisions means isotropic, this thing. So the cross section now becomes independent of theta. So at the lowest collision energy, the diffusion cross section is identically equal to the scattering cross section. Okay, and so these two are the same. Now there's another bit of, because people have been splitting up the cross sections into charge exchange and elastic cross sections, there's another issue which has come up where it is commonly assumed that the diffusion cross section is twice the charge exchange cross section. And this has to do with some Langevin type of argument. And here you can see lithium 6 and lithium 7. Lithium 7, this is indeed true because the twice charge exchange plot is coincident with the diffusion plot. But for lithium 6, these two separate by a huge margin. And so I'm just cautioning people that you have to be much more, things have to be a bit more, you have to take these things with much more care if you are going to do be in the full quantum regime. Okay, so this is what I would like to say. So now diffusion by collisions is also something that we can kind of understand. So now let's talk about a new kind of diffusion, which is diffusion by hopping. Now, so let's visualize the system first. You have a single positive ion in a cloud of atoms. Okay, and within this cloud of atoms, okay, you have this ion. It has been created by just, very gently pulling out one of the electrons of the atoms so as to get an ion which is thermal in terms of its kinetic energy with respect to the rest of the ions, rest of the atoms. So the ion is the charge now inside an ultra-cold gas at low enough temperatures and high enough densities. And it's kind of, this is an experimentally accessible regime. The wave packets of the nearby ion and atom, they start overlapping. Okay, so this means that the ion and the atoms, as you are cooling them down, they delocalize, and they are not exactly these point objects, but they are situated with a certain physical uncertainty of where they actually exist. Now, so what happens is these clouds overlap, and these are two views, and this gives rise to the possibility of charge hopping, okay, which is in addition. This is not collisional. This is in addition to collisional diffusion. Okay, so this hopping. So now what do I mean by this? So let's say that you're at a very low temperature. So you have a de Broglie wave. Okay, so you have a certain delocalization length, which is lambda A for the atom, lambda I for the ion. Since the ion is done by gently removing one electron from the atom, basically lambda A is equal to lambda I. We work in that scenario. Now, the spacing between these two, the average location of the wave particle, where the wave packets are centered, is separated by a distance L. And what you have to then calculate is the probability that if I have an ion at a particular location consistent with my ion wave packet, what is the probability where I can get an atom within that volume, within a volume described by a radius rho IA, which is given here. So rho IA is some distance scale, and we need to compute this particular probability. All right. Given that we have computed this probability, what can happen is the following. You can then mediate an exchange if you are within the exchange. So you have to basically, if that probability is reasonable, and it is, then exchange can occur. And this is what happens if the atom and the ion are very far away, where L is much, much less than, where lambdas are much, much less than L. No, there's basically little or no exchange possible. But when lambdas are of the order of L kind of thing, then an exchange takes root. And so if you look at a cloud of atoms, which is here, and you ask, okay, I start an ion at the origin, how does the ion evolve through this mechanism? Then essentially it's a question of the probability of wave packet overlaps and the distance and the attainment of the distance where exchange is possible versus the exchange rate, into the exchange rate. And that's basically what you have to compute. And that is precisely what we do. So this is the ion atom. I think I've lost my video again. So this is the ion atom.
Just now, Sadiq, around
Right. Can you trigger it because it gets triggered? You triggered it the last time.
Okay, let me try.
So the hop rate is given by the probability of the ion and atom at a particular rho IA and into the exchange rate, okay, which is given by the exchange energy divided by H, and you integrate over rho IA and you get the thing, and you get the average hop rates, and you can see that for a few 10, from a microkelvin to a few 10 microkelvin, you can get sizable charge hop rates in lithium atoms for densities which are of the order of 10 to the 19 per meter cubed. Okay, so 10 to the 19 per meter cubed is like dense mott kind of this thing. It's not yet a Bose condensate. Okay, so yeah. Right.
Yeah.
Thank you.
Okay. No problem.
Right. I do not know what's happening. Okay.
No,
with respect to this.
Yeah. It just
so
saw. Yeah. Right. Yeah. Go ahead.
So now what is very important is that we need to now determine what is the collision rate versus charge hopping rate. So you have two mechanisms. Now there's a collision rate, which is the product of the collision cross section into the velocity thermally averaged into the number density. That is the average collision rate that an ion will suffer, a single ion will suffer. N is the number density of the atoms. And the collision rate coefficient is basically Z divided by N. And the hop rate is similarly V bar, which is the hop rate, which was determined on the previous thing, divided by the number. And what you find is that the hop, so these are the red ones, the red, yellow, and blue are the hop rate for discrete particles. The green is for if you assume that the atomic gas is a continuum, but let's not worry about that right now. These are hop rates for discrete particles, and so as you are increasing the density, this is the highest density, N1, okay, 1019, and this is the collision rate. And you can see there's an order of magnitude, and even more than an order of magnitude at different points on the temperature scale of difference between the hop rate and the collision rate, where the hop rate is dominating. And this is important. So now, but that's not the whole story, because unfortunately the diffusion is a very peculiar phenomenon. And since we are going to be detecting a diffused ion, so the collisional diffusion coefficient goes as 1 over the number density. But the collisional diffusion, the hopping diffusion goes as the number density of the atoms. So while we can take great comfort in a graph like this, where you see a clear advantage of hopping, actually when you get down to it, the range in which hopping will dominate collisional diffusion is far less in this thing. So here you can see, let's look at just the green line. These are for two different densities. So this is the hop rate, okay, and this is the diffusion coefficient for hopping.
Sorry,
and this is
there is a question here. Do you want to take?
Yeah.
It's from Arnab Sarkar. He says, for any kind of heteronuclear collision, escape rates of ions should be the same then, is what he's asking you.
For any kind of heteronuclear?
Yeah.
I'm sorry, I didn't kind of understand this question because heteronuclear is we are talking about a homonuclear system.
Yeah.
So I'm not understanding what the context of this question is.
Actually, initially you showed a collision, like the rate of escape when both are cesium atom. One is ion and a cesium atom, and another case that is a different atom.
Yes.
So for cesium atom, the escape rate was very slow. So my question is that when this is not not a cesium but any other atom, the escape rate should be same.
So just okay, that experiment does not connect with this one because that is not a diffusion experiment. Okay, it is a collision experiment, but it is not something in which the diffusion is being talked about. Here, the situation is like this. You have a slab of atoms, okay? You have a volume of space where there's a uniform density of atoms, and you're starting ions from a particular point in this density, okay? And you are seeing how where the ion is going to be at a particular point. Let me just go to the next slide, and then you will kind of understand perhaps a bit more about what I'm saying. But the diffusion, see, if you look at this particular thing, if you look at the average collision rate, okay, you look at this. This is what is going to dictate the collisional diffusion finally, okay, and it's going to be a product of the total cross section and the velocity. So in a heteronuclear thing, it will scale as whatever is the cross section. Okay, if you have a large cross section, then the collision rate will be higher. If you have a small cross section, the collision rate will be lower. That's basically it.
Okay, Arnab, if you have further questions, then you can do it at the end of the talk. Yeah.
Yeah, sure.
Right, I'll continue then. Yeah. So now let's go to a particular instance where there's diffusion in a Gaussian distribution of atoms. Okay, so let's say that there's a Gaussian distribution of atoms which is given by n, which you are seeing there on the screen, and you have an ion which is initially starting at the origin of this Gaussian distribution, and its time coordinate is going to be given by xg, yg, zg, which is basically means that it is with respect to the origin of the Gaussian ensemble. So now this is where, so this is the thing, this is a rough emulation of Gaussian distribution of ions, and what you're doing is you're starting an ion which is in thermal equilibrium with this cloud of atoms, okay, at the origin, and then you are going to ask the question that it's moved here in time, and how has this diffusion occurred. Okay, so how does the ion diffuse? Now we know that we have two different diffusions which are available in this scenario. So now let's look at the diffusion coefficient. As I told you, there are the diffusion coefficient for the hopping is different from the diffusion coefficient of the collisional diffusion coefficient, and you can see this now. So the diffusion coefficient of the hopping is essentially very large at the origin, okay, where the density is high, and it goes down very rapidly, okay, and at around sigma it goes under and the diffusion becomes negative, okay. And this is kind of pretty straightforward, because you know the diffusion is going to preferentially go seek out the higher density to hop to. So when it goes beyond when the density gradient really starts mattering, the hopping is preferentially towards the higher density than the hopping you know, just making more distance from the origin. On the other hand, collisional diffusion with the coefficient is going to, so this is basically as a function of the radial separation, and is going to increase monotonically, all right, up. So what happens, what you would see in this scenario is a competition between collisional diffusion and hopping diffusion. And what hopping diffusion does, okay, if you take which is the blue dashed curve, what hopping diffusion does is that if there's an ion here or anywhere in this part, it will tend to move inward to the zero diffusion point, where the diffusion coefficient is 0. And the ion which is located here in time will move to again a point where the zero diffusion is there. Now, since the atomic collisional diffusion is quite small, the crossover point is somewhere here, but you have another crossing of the effective diffusion coefficient, which is the sum, the geometric, which is just the sum of these two diffusions, which is essentially gives you another crossing. Which means the following: if you, in a system where both these things are simultaneously operational, then essentially any ion in this regime, within this radial distance, will tend to diffuse onto this particular point where its diffusivity goes to 0. This can be appreciated from this vectorial kind of a plot, where you know here you have inward diffusion, here you have an outward diffusion, and beyond this point you get a net outward diffusion, because again the collisional diffusion is stronger and overwhelms the hopping diffusion. So this is very useful, because what is happening is that the ion which is seeking the point where its diffusion in this gradient of gas goes to 0. Okay. So when you can do a Monte Carlo simulation, I've lost video again. So you can do a Monte Carlo simulation, and
you're frozen, Sadiq, you're frozen.
Oh my gosh. Okay.
Yeah, but we can. Yeah, let
can you
me
hear
try the
me?
same. Yeah, sure.
Right.
Yeah, we can hear.
So, okay. So the point is that we have you can do a Monte Carlo simulation, and you find that, yeah, sure enough, the ions go up and down, but they essentially flatten out at this particular high gradient point. Okay. And so you start, yeah. And this is the ballistic curve. Okay, so if you had started an ion at the origin with roughly with the same thermal velocity, which is the average velocity of.
We are stuck on a different slide.
Yeah, you're frozen, Sadiq. I think we are lost him. I'm just calling him on the mobile. Yeah.
Hello, can you hear me?
Sadiq, we can
Right.
hear
Yes,
you.
I can.
I'm so sorry. I do not know what happened, but everything glitched out.
You
I'm
can
going to
start
screen share
sharing.
again.
Yeah.
Okay. Hopefully it's not too much of this thing. Okay, just 1 second. So yeah, so essentially what happens is yeah, so the ions tend to stabilize at the high gradient point. This is the ballistic expansion of the ballistic trajectory of the ion, and what you find is something very interesting, which is that at small times, okay, you have actually the diffusion due to hopping is super ballistic, all right, and then it kind of becomes subballistic in the longer time. So it really tries to find the point of largest gradient very fast. Okay, so of course we are experimentalists and we want to know how this thing will work in a laboratory. So what is very important is in a lab you have stray fields. And the question is that when you have a stray electric field, what happens in this situation? So we have done the similar study for an ion in a stray field with hopping and without hopping. So the ballistic one is just going vertically up. You can see this. But the ion and the electric fields that we have taken are definitely above the values at which are at the state of the art of control. This is at least an order of magnitude better than that. I mean, higher than that. So this kind of control of electric fields is indeed possible. And you can,
maybe 2 more minutes because
yeah.
7:45.
I'm done. I'm done.
Sure. Yeah.
Okay.
Thanks.
And you can still see that you can get a plateau. And of course it moves out, but you should be able to detect it, and you can do it for higher fields, and you can still see that the residence time of the ion in the trap region is quite in excess of what you can actually reasonably experimentally do. I've lost my video again, but I think we can manage. So anyway, the point is that it is completely a doable scenario. It is experimentally valid, and therefore this is what we work towards, and this is the experiment we built. In order to do that, this is our lithium experiment, or what we call dilithium experiment, and the people who follow Star Trek will understand dilithium quite well. In any case, so this is our lithium mod. It's still a bit hot to start these kind of experiments with. And then we have a microchannel plate, and we have electrostatic and magnetic lensing here, which will allow us to positionally determine where the ion is. So we are all set to do this kind of experiment. And so let me just wind up with a few takeaways. And the takeaways are this. So it is extremely important to make the hybrid trap. These experiments started as hybrid traps. You trap ions, you trap atoms, and put them together. The synthesis of the hybrid trap experiment is essentially in putting an ion as the impurity in a larger cold gas. This is something which can be done with an alkali atom, because there may be like between 10 and 20 hybrid trap experiments in the world, but there are like maybe a few hundreds to 1,000 cold atom experiments in the world. And this particular manifestation allows the community, which is a cold atom community, to do hybrid, to do ion atom work. We have already seen from Tillman Fau's lecture the first one in this in this school. We've already seen from there that how this kind of stuff is possible. This is our analysis is not in the degenerate gas regime. Okay. Important thing is an ion trap is not required in this particular case. In this conception of the execution, the diffusive trapping is achieved at the high gradient points, and S-wave regime is also doable in this from this pathway, as well as impurity driven physics that we have been learning about during the school. With that, I will just sign off with credits to all the people who have been working on this. Thank you.
Thank you, Sadik. Now the floor is open to questions. People who want to ask a question can unmute themselves and please ask.
So maybe I can ask something, Sourav here. So
yeah.
You at your densities, I mean, 10 to the power
19.
18.
Yeah, 18, 19. We can do it at 18 also.
Right.
So
but the thing is, what about three-body collisions and all?
Ah,
I mean,
okay.
Not the,
Yeah. So three-body collisions are obviously a very big deal. And what is this? What has been done here is we have taken into account overlap with multiple atoms in the neighborhood, but three-body collisions, when you evaluate it. So for instance, when you evaluate the three-body collision rate, for every 1,000 hops, you get a few thousand hops, you get one three-body. Okay. So the way forward obviously some fraction of events will turn into molecule, the three-body processes where you can create a molecular ion or whatever. And you have a third body to take care of the energy momentum conservation and things like that. But there will be a large, you can always work in post-selection, and this seems completely doable. So it's a factor of 1,000, better than a factor of 1,000, few thousands.
And what temperatures are going to be at to see this?
So practically it's between 1 and 5 microkelvins at these densities. So it's going to require some work. The point here is the following. This analysis, I've explained the reasons why we picked lithium. Okay, because it gives you the highest temperature. But actually this need not be the case. You can now go and repeat this analysis across many alkali species and figure out which one is the appropriate species for this class of experiments. The reason why, so the point is that part of our thinking is about raising the temperature so that the ion trap temperatures are coincident with the atomic temperatures and everything is quantum. But that need not be a handicap if you are going to not go for an ion trap in the first place. What you need in principle is to shield electric fields and let loose a threshold ionized atom into a gas into an ensemble. So I would say you do away with the ion trap, and that is actually the power of this. So therefore the cold atom community can actually just jump into this.
Yeah. I think we have time for just one more question. Saikat, you wanted to ask?
Yeah, Sadik, it might be a little wild, but just this collisional phase shifts that one picks up, particularly if one can control, can one actually make gates, or are there thoughts on that?
So we are going to do so right now. With who knows how the pandemic goes, but we have an experiment which we are building up to actually investigate a single atom, single ion. Okay, interaction, right?
Yeah, that's the regime mounter.
Yeah, exactly. So that is being actually, we are working on all that. The experiment is in some superposition state of order and disorder. I mean, order means, importing stuff to get the experiment going, and disorder is our own thinking. And some level of conceptualization has already occurred. In fact, the ion trap is now being designed, and which is good because this is going to be a precision ion trap. And so we do expect to get into those regimes also.
Okay. Thank you.
Great. Now let's thank our speaker. And yeah, is there a clapping noise which is recorded? Oh, no. Okay. We are clapping for you, Sadik. Yeah.
Yeah, no problem. Thank you.
Yeah, great. So our next speaker is Professor Tanya Zelevinsky. Professor Tanya, are you here? Hi, Professor Tanya, are you here?
Hi, hello.
Hi, welcome. So,
thank you. So let me try to share, right? Share the screen.
Yeah, after you share, I'll introduce you and then you can start speaking. Yeah. Great, we can see your screen, yes.
And you can see it. You can see it now.
Yeah, we can see it now.
Okay. Yes, I will not use my laser pointer because it causes it to crash. I'll just explain what I'm talking about.
Sure, no problem. So yeah. So our next speaker is Professor Tanya Zelevinsky, and she joins us from the United States. Welcome, Professor Zelevinsky. Professor Tanya graduated from MIT in physics and math and received her physics PhD at Harvard University, where her thesis work involved precision spectroscopy of helium atoms. She joined the faculty of Columbia University in 2008 after a few years of learning about optical lattice atomic clocks at Gila, Colorado. Her research interests involve precision measurements and quantum optics, particularly state-of-the-art optical spectroscopy with diatomic molecules. Today, she'll tell us about her research work on ultra-cold molecule clocks. May I now request Professor Zelevinsky to deliver a talk. Professor Zelevinsky, would you want to take questions during your talk or at the end of your talk?
Yes, please free to just interrupt.
Okay.
Anytime.
So to enable discussions, it'll be nice if you could finish, let's say, 7 to 8 minutes before your time. Is that okay?
Yes.
Yeah. Thank you, and please go ahead. Yeah.
Thank you so much. Thank you for the introduction and for, of course, inviting me to be a part of this event. It's my pleasure to talk to you today about our work at Columbia on ultra-cold molecular clocks. As you know, quantum science with molecules has become a very exciting field recently, and it helps us go beyond what we can do with cold atoms in learning about basic chemical processes, also with designing quantum materials and quantum information and computation processes, and even enhancing our work in the most fundamental aspects of physics. And these subfields are not completely disjointed. They share a lot of common challenges. For example, in order to create good qubits and to build very good clocks, one needs to ensure very long quantum coherence times between quantum state superpositions. So a lot of these subfields, a lot of this work with cold molecules really share common challenges. And this concept of long coherence times is definitely a theme in the work that I'll tell you about today. So here are a few of the questions that we address through the research that I'll talk about. We would like to understand if small molecules can contribute to our understanding of fundamental forces. And this includes both new, so far undiscovered physics, as well as old physics, such as QED, which plays a critical role in high precision measurements, and also in our understanding of atomic and molecular structure. We're also exploring whether it's possible to control molecular states across a large range of the electromagnetic spectrum, and how to decouple their internal dynamics from the environment for the most precise quantum control. Finally, we are also investigating whether there is a metrological advantage for using molecular versus atomic systems. The first task in working with ultra-cold molecules is, of course, creating them. Two different pathways can be used to create samples of molecules at microkelvin temperatures. One method is to directly cool molecules with an alkaline earth metal optical cycling center. So these are metals from group 2. This metal is typically bound to a halogen, such as fluorine, or to hydrogen. And it's even possible to substitute the halogen or hydrogen with a larger functional group, which can give access to polyatomic molecules. And the second method is to laser cool atoms, usually alkali metals in group 1. And these ultra cold atoms are then assembled into diatomic molecules in their ground state using magnetic or optical fields. But alkaline earth metals in group 2 have many features that are very attractive for both laser cooling and metrology. And these features also transfer onto bound molecules that are composed of these atoms. But on the other hand, these atoms don't have unpaired electron spins and are difficult to control with magnetic fields. So we have solved this difficulty by using all optical methods to create ensembles of diatomic strontium molecules in their ground state. So these are unique ultra-cold molecules with purely van der Waals interatomic potentials. So these ultra-cold van der Waals dimers, strontium-2, have two key features to keep in mind. But first, I'll briefly refer to the molecular potentials here on the left. There's the ground state potential, X singlet sigma G, and the lowest lying pair of potentials with the threshold at the intercombination line of strontium. So this intercombination line corresponds to the singlet S to triplet P1 atomic transition. And the pair of the potentials is called 0U and 1U. So one important property of the molecules is the presence of very narrow optical transitions that are of this singlet triplet type. And this provides a powerful capability for quantum state control. Also not shown here is another series of optical transitions. I'll mention them later, G to G transitions that are super narrow because they're forbidden by the molecular inversion symmetry. And the second important property that I'd like to point out is the completely spinless molecular ground state for bosonic strontium isotopes. And the relative simplicity of this potential is certainly an advantage for precise metrology and ab initio calculations. So to illustrate the point about the ground state van der Waals potential, here you see the ab initio calculated potential shown with red points, and the experimental potential derived from traditional spectroscopy shown with the blue line. And there is a very good agreement at the level of 1%. So as I mentioned earlier, one way to create ultra-cold molecules is to assemble them from atoms that are laser cooled to microkelvin temperatures and assemble them using light or magnetic fields. So our strontium dimers are created by optically making excited dimers, which then spontaneously decay to the electronic ground state of the molecule. And since the photons take away the binding energy, the resulting molecules are still at a few microkelvin. And since strontium atoms are non-magnetic, we use only optical techniques to create the molecules. The molecules are trapped in a one-dimensional optical lattice, which is just a standing wave of retroreflected light. Initially, the lattice holds the atoms in the bright microtraps, or lattice pancakes, as we call them. And then the molecules are also created in this lattice, preserving the original microkelvin temperature. And any probing light propagates along the lattice axis to strongly suppress any Doppler dephasing. This is the setup we use to create the strontium molecules by laser cooling an atomic beam that you can see near the top, and then trapping the atoms in an optical lattice and photoassociating them. This picture is actually a bit outdated, but now about a dozen laser systems are used for creating, trapping, and probing the molecules. I mentioned that the strontium molecules give us access to very useful narrow optical transitions. So I'd like to expand a bit on what we have gained from these forbidden transitions, especially the insight into basic molecular physics. Here is a schematic of an optical transition from a rotation-free level in the ground electronic state to a singly excited level near the intercombination threshold. This upper level has a Zeeman splitting in weak magnetic fields of a few Gauss, kind of a typical atomic level size Zeeman splitting. And from the linear Zeeman shifts, we could very precisely determine the mixing coefficient between the two potentials, the 0U and the 1U, that converge at the intercombination threshold. And here you see a typical Zeeman spectrum. And you also notice that it's extremely asymmetric. It turns out that this is the case because of the huge quadratic Zeeman shifts. And these exceed the quadratic Zeeman shifts in strontium atoms by a factor of 1,000,000. And you can clearly see the curvature even at a couple of Gauss on this plot on the right. We found that this behavior was strongly linked to the long-range dipole-dipole interaction. And this unusual behavior of the Zeeman shifts sometimes was a stronger test of the molecular model than spectroscopy alone. And I think it also nicely shows a striking difference between a weakly bound dimer and just a pair of atoms. This intercombination transition has also proven to be an incredibly useful tool in imaging the molecules and studying quantum state resolved photochemistry. In this case, the optical transition is from a ground state bound level to the singly excited continuum, and potentially back down to the ground state continuum, where the molecule is split into its fragments. On the bottom left, here is a photodissociation spectrum, which is very narrow because of the long-lived excited continuum. And the images show the side view of the emerging molecular fragments. But when we image these exploding molecules by looking into the symmetry axis of the trap, we observe non-classical angular distributions that show matter wave interference, as you can see on these calculated and experimental images on the bottom. This type of interference is really a key feature of ultracold reactions. The quantum state of the fragmented molecule is entirely determined by the well-known initial quantum state of the molecule and the photons. And by selecting their quantum states, we can control the shapes of the resulting partial waves. And we have also used this technique to probe the continuum with a high sensitivity to features like reaction barriers and collisional resonances. Here are a couple of specific examples of quantum interference effects in ultracold photochemistry. The strontium molecules are dissociated into the ground state continuum, such that all the outgoing quantum states are known, as well as their relative phase. So in both these cases, we are essentially imaging different coherent superpositions of G-wave spherical harmonics, which result in 8-fold fragment patterns. So in both cases, the experimental images are shown on the top right of each square, with the calculated predictions illustrated in 3 different ways. This long-lived intercombination threshold also gives rise to a completely new type of super narrow optical transition in the molecules, which is absent in atoms. This is a transition to the state with the same inversion symmetry as the ground state, which is even or gerade. The transition mechanism is magnetic dipole, and the strength of this effect is proportional to the bond length of the molecule squared. And this results in 2 families of excited molecular states, super radiant, which are still quite long-lived, about 10 microseconds, but their decay is electric dipole allowed, and subradiant with lifetime of order 10 milliseconds. These subradiant states provide a really nice handle for optical control of the molecular quantum states. So here we have a coherent optical Rabi oscillation on the left, and on the right is a measured lifetime approaching 10 milliseconds for a subradiant state. These subradiant and other long-lived excited states in molecules also provide very interesting opportunities for metrology that we would like to explore. The subradiant states are extremely useful for working with molecules that are trapped in an optical lattice. We can take broad spectra of these states and see the expected red and blue lattice trap axial sidebands. That's in addition to the narrow carrier in the middle. And these precise measurements of the axial lattice trap frequency allow us to precisely calibrate polarizability measurements for different molecular states, which is important for coming up with optimal designs for molecular clocks. Also zooming in on the carrier and measuring its asymmetric width directly gives us the temperature of the molecules. And jumping ahead for just a moment, we can also see lattice sidebands with 2-photon Raman transitions between levels within the electronic ground state of the molecules. In fact, we can hide the sidebands in the clock mode when we use co-propagating Raman laser beams, or we can reveal strong sidebands in the counter-propagating configuration. So we can measure the molecule temperature directly by using the sidebands, even without using narrow atomic transitions or narrow molecular transitions that are 1 photon. While on the other hand, we can suppress the sidebands and the associated line pulling that could disturb the operation of the clock. Okay, so far, I described high resolution spectroscopy of the molecules that are weakly bound, which is how they are initially created from the laser cooled atoms. But to make the best use of the molecular clock, it's important to be able to create molecules in the absolute ground state. In fact, we can now create ground state strontium-2, which is the first ultra-cold molecule of this type. And to do this, we momentarily switch off the lattice, and this removes decoherence from the light shift and results in very narrow EIT signals like the one shown here. EIT here is electromagnetically induced transparency, where the pump and probe coherently connect the highest and lowest states within the ground state molecular potential. So in this free space environment, we implement a stir-up or stimulated Raman adiabatic passage. So initially, all molecules are in the most weakly bound state, which we call V-1. Then the resonant or near resonant Raman lasers are smoothly pulsed on and off to transfer the molecules to the ground state, which is V0. We cannot see the deeply bound molecules directly, so we reverse the stir-up process and recover the molecules in the weakly bound state. And from the number of the recovered molecules, we deduce the one-way transfer efficiency, which in this plot is about 75%. More recently, we have achieved over 90%. And the black line is a simulation based on the optical block equations. And here is the conceptual implementation of the molecular clock. It involves a pair of vibrational clock states that each see the same trap depth in a so-called magic optical lattice, and these are coherently coupled to each other. So since direct vibrational transitions are strongly forbidden, we drive a 2-photon or Raman clock transition off resonantly coupling to a long-lived excited molecular state. Here, this calculation shows the intrinsic lifetimes of various clock states as a function of their binding energy in the ground state molecular potential. So the contributions include natural decay channels and also black body excitation at room temperature. And the net lifetimes shown with the gray points in the lowest trace generally exceed 10 to the 5 years. So the clock state coherence will be set by technical limitations. So here, the details of the ground and excited molecular potentials are shown in more detail. So the absolute ground state is bound by approximately 1,000 wave numbers, and both probe lasers in the Raman configuration and the optical lattice light are phase locked to an optical frequency comb. The clock states 1 and 2 are vibrational levels in the ground state. So here 1 is the most weakly bound, while 2 is deeply bound. The clock states are coupled by a coherent Raman transition. The Raman transition is via an off-resonant intermediate excited state. And the optical lattice frequency, shown with the dashed yellow line, is red detuned from that intercombination threshold. So now let's focus on the relevant quantum states. In orange and blue are the upper and lower clock states, which have vibrational numbers 62 and 6 in this example, and no rotational angular momentum J. Moreover, the lattice is near resonance with a transition from state 2 to a deeply bound, long-lived rho vibrational state in 1U. So this state is highlighted in green. When the molecules are in an infrared lattice, the clock states are both downshifted in energy, and the molecules are optically trapped. But generally, though, the clock states will see different trap depths, and the clock transition is light shifted and broadened due to
Professor Zelevinsky, there's a question. Would you like to take it now?
Oh yeah, I'll take a question.
Yeah, I'm just seeing it about 7 minutes later. Yeah, the question is from Saikat Ghosh, and he asks why the subradiant states decay. Is there any dependence of the subradiant states with total number n, or is it just single particle effect?
Yes, this is two body subradiants. So just subradiants between the two atoms that make up a molecule. So two body, but a single molecule effect. It's not a mini body effect in this case, but it is still subradiants because the physics is similar. It's sort of a suppression or a destructive interference of spontaneous decay between the two atoms, each of which could be the excited one. So because of this suppression, there is the electric dipole decay is completely suppressed. But in a molecule, you develop a new mechanism that can occur because of the finite bond length. And so you can get a weak magnetic dipole transition, and that's why they can decay. So that's the fundamental reason they can decay. And also we found that there's even a faster decay process, which is non-radiative or pre-dissociation. Still very weak, but a little bit stronger than the magnetic dipole. But the electric dipole should be perfectly suppressed.
Okay, thank you. Thanks.
Mm-hmm. Sure. Great. Yeah. So so about the clock states, so they're both downshifted in an infrared lattice, but generally the two clock states will see different trap depths, and also the clock transition is both light shifted and broadened because of the thermal spread of the molecules, and the two quantum states see slightly different traps. But when the lattice frequency is deliberately blue detuned from the green intermediate state, then the AC Stark shift pulls the blue and green states slightly closer together. And at a specific lattice frequency, this trap depth U for clock state 2 exactly matches the trap depth for clock state 1. And this is the magic wavelength at which the clock resonance then sharply narrows, since it's no longer limited by the inhomogeneous Stark broadening. One way to search for a magic wavelength is to measure the clock shift versus the trapping light power at various wavelengths shown here in different colors. And the wavelength with zero slope is magic, which is the red line here. Okay, so as we sweep the lattice frequency through that narrow 1U resonance, we can directly measure the AC Stark shift of the deeply bound clock state 2. So here we change the lattice frequency from 5 gigahertz below to 5 gigahertz above the resonance and see the dispersive Stark shift curve. The green bar shows the lattice detuning where the polarizabilities of the two clock states are equal, which corresponds to the magic frequency. And here is where we expect to see the narrowest clock resonance or the longest coherence time of the clock state superposition. And here we directly plot the clock resonance line width. As you see, the baseline shows a nearly 100 kilohertz width due to lattice-induced broadening, and the line width increases further as we approach the resonance. But at the magic frequency value on the blue side of the resonance, it drops dramatically by over 3 orders of magnitude. So here are a couple of clock spectra on either side of the resonance, but both away from the magic frequency. And we see the expected light shifts and broadening from the lattice light that are both on the order of 100 kilohertz. But at the magic frequency, the resonance is symmetric and very narrow. So this is the zoomed in spectrum of the vibrational clock resonance at a magic lattice frequency. This resonance is 30 hertz wide, which is a 3,000-fold improvement over a non-magic lattice wavelength. The resonance frequency for this clock state pair is 25 terahertz. So this spectrum corresponds to the quality factor of 8 times 10 to the 11. Besides using the narrow width of the clock resonance to quantify the coherence of the clock states in the magic lattice, we can directly drive quantum Rabi oscillations between the clock states. So essentially, the molecule is made to oscillate between its tightly bound state and its weakly bound state with a long bond length. And a well-chosen magic frequency helps us reach very long coherence times for the molecular clock. So here's a Rabi oscillation between the molecules in vibrational states that are separated by nearly 30 terahertz. The oscillation decays with a long time constant of 130 milliseconds. So we're not yet limited by the two-body collisional lifetime of the molecules that's shown here with purple triangles for the upper clock state. But instead, we are currently limited by the lattice-induced loss of molecules in the lower clock state, shown here with the red squares. And here's a more, yes?
Sorry. Would you like to take one more question?
Yes.
Yeah, this is being asked by Professor Saikat Ghosh. He asks, why is it magic? Is there cancellation of light shifts for so many levels too?
Yes, so back for a moment to here. It's magic for the two clock states 1 and 2, because the lattice that connects state 2 to this excited state shown in green, it pulls the blue state up because of the Stark shift between the blue and green states, and then it matches the frequency of the clock states. So the trap depths for the two clock states marked as U are exactly the same. And that happens at a specific frequency, sort of on the blue tail of the lattice-driven resonance, which is a couple of gigahertz to the blue of the resonance. And so so that's exactly when the line width narrows in the middle plot. And here is where we see this narrow resonance. And also here is where we take the Rabi oscillations for the longest coherence times.
Thanks.
Yeah, so we are very happy with this 100 millisecond coherence of states that are separated by tens of terahertz. But still, we are interested to extend them even longer for even a better clock. So we take a more careful look at the lifetime of the deeply bound clock state 2, which is the one that limits the coherence time of the fringes. So if we put the lattice frequency away from this magic value, meaning quite far from any lattice-driven resonance, then the decay of that state just shows a typical two-body decay, with more than half of the molecules are still remaining here after 100 milliseconds. So this is the green trace. And the magnitude of the two-body loss coefficient beta is quite typical for ultra-cold molecule systems. But at the magic wavelength, shown with the magenta trace, the loss is much more severe, with almost no molecules remaining by 100 milliseconds in this case. And this magic lattice loss is exponential rather than two-body, potentially indicating lattice light scattering. But from our knowledge of the lattice-driven transition, we were not expecting such fast loss. And this rapid loss can be studied as a function of lattice light intensity, as shown in this inset. So you can see that the loss rate, or the scattering rate, does increase with the lattice intensity, which is the x-axis. So the lattice light is a limiting factor. However, the scattering seems to increase quadratically with the lattice power, which is the red line parabolic fit. And this may point to two-photon lattice-induced photodissociation. So with our theory colleagues, we have looked into this process and found that it should most likely be weaker than what we observe here. So this rapid lattice-induced loss is not entirely understood. However, we do have a way to design the clock to minimize this loss by choosing an optimal 1U state for the lattice-driven transition. In other words, we look for a magic frequency where the lattice is more detuned from a resonance. And in practice, it should be detuned by more than 1 gigahertz, which can help with a number of technical issues. So how do we choose the best magic wavelength? So this plot uses colors to show the coupling strengths, or a transition dipole moment squared, DMS, between the ground state vibrational levels, which are all potential clock states on the vertical axis, and 1 U excited states on the horizontal. The brighter colors indicate stronger coupling, and we see a typical pattern with kind of 2 main branches, which arises because the molecule spends the most time at its inner and outer classical turning points. And since we're interested in at least one deeply bound clock state, here I zoom in on the lower left corner that shows coupling strengths for the lowest 10 vibrational states. So near the bottom of the potential, the energy structure is fairly harmonic. And this shows up in this checkerboard pattern of low and high transition strengths. So our first experiment used the state pair highlighted with the white square. And it's relatively strong, but it doesn't sit on one of the branches. And for the next iteration, where we obtained the Rabi oscillation that I showed today, we chose the black square for the magic lattice, and the oscillations lasted 4 times longer. And I would like also to highlight that identifying this checkerboard pattern of lattice-driven transition strengths really helped us with the spectroscopy of the excited state and with assigning quantum numbers to the spectra. So there are over 120 states in the excited 1U potential, which means that despite the 1% precision of the ab initio calculations, we still can't be sure of the state's vibrational quantum number only from its binding energy measurement. But this distinctive pattern helps us identify the correct vibrational quantum number for the excited state. And here I show calculations corresponding to row number 6, and also precise measurements of the selected transition strength. So we find that there is a unique way to combine energy level spectroscopy with transition strength to get the correct quantum state numbering. And the magic lattice detunings that are measured and shown in the bottom plot. And the largest detuning with the arrow has produced the longest Rabi oscillations. And very recently, we found a magic wavelength with a detuning.
Excuse me, here is another question.
Yes.
It's asked by Bimalendu Dev. So is it possible to find a magic wavelength to trap both a molecular state and free atom dissociated state?
Well, usually a magic wavelength is, a lattice can be magic for a particular pair of clock states. It's very unlikely that you can find something that's magic for more than 2, like 3 states. Usually we don't find it's necessary because there's one clock transition that you want to really enhance the precision of. And the rest, you just need to be able to do some manipulation. So you want to choose something without too much broadening, but true magic wavelength is usually necessary just for a pair of states. Of course, in this case, in the case of molecular clock, there are many potential clock transitions, and it would be great to have a magic wavelength for more than just one pair. But that's not usually easily possible, unfortunately. But we're still thinking about what is the most practical way to kind of approach that.
Thanks.
Yeah, sure. Great. Yeah. So again, this black rectangle gave us a better result because it's a stronger lattice-driven transition with a larger detuning. And much more recently, we found a magic wavelength with a detuning of nearly 5 gigahertz, which is larger by yet another factor of 2. And in fact, the largest we expect for this molecule. And its transition strength is highlighted here with a red rectangle. It's the brightest one that we can choose. And here we have experimentally found the polarizability resonance with this nearly 5 gigahertz magic detuning. And this magic lattice, which happens to be at 1005 nanometers, we can expect to achieve even longer clock state coherence times. So I'll skip this part. And I'll say here that even our current implementation of the molecular clock is already precise enough to start providing useful results for the dimers of the dominant strontium-88 isotope. So here is a fairly coarse preliminary scan of the bottom of the ground state van der Waals potential, showing the 7 lowest vibrational states. And we also have precise data on the top of the potential corresponding to vibrational numbers above 60. And this data was collected using a 2-photon Adler-Towns spectroscopy, as you can see in the sample scan, where even the initial precision for some of the selected states is already more than 4 orders of magnitude higher than in previous work. A bit more generally, a molecular clock that provides these very precise measurements of the vibrational states is an excellent sensor of the interatomic force. So when the positions of the bound states are known with an uncertainty below, say, a part per trillion, then the interatomic potential and the binding force that holds the molecule together can be reconstructed with a similar precision. And this is, of course, in addition to other exciting applications of molecular clocks, such as metrology in the terahertz regime and measurements of the temporal stability of the electron to proton mass ratio. But regarding the force sensing, this high precision interatomic force sensing can even lead to discoveries of new physical forces. So for example, it may be possible to use the molecular clocks to learn about gravity in the ultra short range. So our strontium molecules can be pictured as pairs of atoms separated by their bond length, which can vary from about 0.5 to 5 nanometers. And this bond length is set mostly by electromagnetic interactions, of course, between all the electrons and nuclei. But since the nuclei are relatively heavy, Newtonian gravity also contributes and makes a very tiny correction to the bond. And possible deviations from the Newtonian gravity can be parametrized, for example, using the exponential Yukawa term with a magnitude A and length scale lambda. From previous experiments that use quasi-classical methods, we know that at the nanometer scale, A is smaller than 10 to the power of 22. So in other words, there could be a huge correction to regular gravity, and it wouldn't contradict any experiments that have looked at interactions between spinless masses. Whereas our molecular clock is a fully quantum system that has the potential to go to higher sensitivities. And from the theory point of view, the possible fifth force would be a small correction to the electromagnetic forces. And in the basic Born-Oppenheimer picture, the energy of a bound molecule consists of the electronic, vibrational, and rotational contributions, although our molecules have no rotational energy. And the strontium-2 ground state potential supports 63 bound states. And the energy corrections beyond the Born-Oppenheimer include adiabatic terms that are proportional to mu, the electron to nucleus mass ratio, and non-adiabatic or mu squared corrections, various relativistic and QED corrections that can depend on both mu and the fine structure constant, and finite nuclear size corrections that implicitly depend on the nuclear mass. And the theory is still under development, but we believe it should be possible to describe the leading order corrections analytically with coefficients that could be partially fitted to the data, isolating mass dependencies that could signal a gravity-like force. So specifically, strontium has 3 spinless isotopes that can form dimers.
Zelevinsky, sorry.
Yeah.
If you can, in 2 minutes, if you can finish, then we can take some questions. Is that okay?
Yes, I will conclude shortly. Yeah, so just one of the last things I want to mention is that strontium happens to have 3 spinless isotopes that can form dimers of multiple mass combinations, supporting a total of hundreds of clock transitions. And these could provide plenty of information on mass dependence across all bond lengths. And also various corrections shown here have different asymptotic behavior with bond length, which can help distinguish, for example, QED effects from new physics. Okay, so to summarize, we have created ultra-cold van der Waals molecules in the absolute ground state. We use these molecules to demonstrate a vibrational molecular lattice clock, which now achieves a quality factor of approximately 10 to the 12 and coherence time of 100 milliseconds across the molecular potential depth, with still a lot of potential for improvement. This clock was first proposed some years ago for measurements of slow time variations of the electron to proton mass ratio, or mu dot. But we're also excited about its applications to sub-part per trillion interatomic force measurements and the potential search for new mass-dependent forces. And finally, I would like to thank my graduate students, my research group who work very hard on these experiments, particularly here, Con and Emily contributed significantly to the strontium work. And also we are very grateful to our theory colleagues, Robert and Ivana from the University of Warsaw, who are working very hard on the ab initio high precision molecular calculations. And thank you very much for your attention.
Thank you, thank you. So now the floor is open to questions. We'll start with Sourav. Sourav, you can unmute and ask.
Oh, hi. So very nice talk. So I was just wondering, to ultimately want the theory to be at the same level as experiment. So at present, how do your experimentally measured binding energies compare with the theory calculated or the vibrational energy? I mean, at what level?
That's right. Yeah. So the theory is still under development. So it's hard for me to say exactly what the precision will be, but I can say for sure that it's not going to be as high as that of the experiment, because if we already have, easily the 30 hertz line widths, which we can average down to well below a hertz, and that's for the largest frequency. Certainly, we can do even better for smaller frequency splittings. And there is no chance right now to have ab initio theory to get to a hertz in a big molecule like strontium-2, even though chemically it's a very simple molecule. So for that reason, here we're thinking about doing a combination of, firstly, thinking about doing isotope shift. Because ab initio, there are lots of non-mass dependent contributions that will be fairly common to the different isotopes. So we'll try to take them out by looking at different isotopic masses and just doing it as a function of mass. So that would be a great simplification. And another thing is that for each mass combination, we have these 60 transitions where all these beyond Born-Oppenheimer terms have a different behavior with the bond length. So as you scan through all the transitions, you get to different bond length, and you can isolate them this way. So it'll have to be a combination of ab initio theory and a lot of data, not only ab initio, because that's too difficult.
So just a maybe related question. So you said van der Waals. So at least theoretically, I mean, is the C6 that you measure, C6 coefficient, does it match with the theory? So I would presume that strontium atomic calculations are quite good, much better than the molecules. So is there a way to at least say that the C6 measured in the experiment will match the theory very well, or no?
That's a good question. I don't have the number specifically on C6, but here I showed just the just a second here. I showed the ground states very roughly. It's a very small picture, but it's a calculation here on the bottom right. The ground states ab initio. This is not really fitted, and then experimental, not from our experiment, but from more traditional or less precise spectroscopy. And for ab initio, 1% or below 1%, that's a very good agreement. But of course, that's very far from what we need. So we're going to these well beyond Born-Oppenheimer terms. But for us, we worry not just about this tail, right, the long range tail, but actually about the entire potential.
Yeah. Thank you very much. Yeah.
Sure.
Professor Bimalendu, can you unmute and ask the question?
Okay. So the upper clock state seems to be excited vibrationally, and it is in the high vibrational level. So is the vibrational relaxation not a problem in this context?
Right, is what not a problem?
Vibrational relaxation.
Yes, so this is the calculation here of the lifetimes that include black body excitation and natural relaxation. And if you, the net, so these are different contributions, but the net lifetimes are in the bottom trace in gray, and they're all measured in multiple years. So it's very, very slow.
Okay, thank you.
Yeah, sure.
Any further questions from the audience? Okay. If not, let's thank the speaker and thank you so much.
Yeah, my pleasure.
Our next speaker for this session, the final speaker for this session, is Professor Subhadeep Gupta.
Hello.
Hi. So, yeah. Hi. So, could you just start sharing the screen so that then I'll introduce you, then you can come.
Of course.
Thanks. Yeah.
Can you see it?
Yeah, now we can see.
Great.
Great.
And you see the full screen?
Yeah, we can see the full screen now. Great. So let me just introduce the speaker. Our final speaker for this session is Professor Subhadeep Gupta, and he too joins us from the United States. Professor Subhadeep Gupta did his PhD at MIT, Massachusetts Institute of Technology, studying quantum degenerate Bose and Fermi gases. His postdoctoral tenure was at University of California, Berkeley, studying, amongst other things, cavity nonlinear optics using collective atomic motions. He joined the Department of Physics, University of Washington, Seattle in 2007, and is currently a professor there. He heads an experimental ultracold atomic physics group, which uses quantum degenerate bosonic and fermionic gases of lithium and ytterbium to explore a wide range of quantum mechanical phenomena. Today, he will tell us about tuning interactions in ultracold gases, superfluid mixtures, molecules, transport. Professor Gupta, would you like to take questions at the end of your talk, or in between is also okay?
In between is also okay.
Okay, great. So if you can finish the talk, let's say 5 to 6 minutes earlier than the allotted time, it will be very nice for discussions. Yeah, is that
Great.
Okay?
Yeah,
thanks.
that's fine.
Yeah.
That's fine.
Please go ahead, start the talk.
Okay. Thank you so much. So it's great to be here in this virtual format, notwithstanding. As introduced, I'm Deep Gupta. I'm at University of Washington in Seattle. I actually grew up in Kolkata, and just a short walk from the IACS in Jalapur. So it's attending a conference in India is like going home. I understand this pandemic situation, everything's become virtual, and I thank the organizers very much for putting together this great conference and for including our work in the program. I'm very happy to be here. So I'm going to be talking about a few experiments in our group, which has the theme of tuning interactions in ultra-cold gases. In the first one, I'm going to be discussing realization of two-element Bose-Fermi double superfluid, in which the interatomic interactions are through a Feshbach resonance between two spin states of one element, in our case lithium, which creates the Fermi superfluid. In another work, I'll tell you about our experiments on combining ytterbium and lithium atoms. And here the interactions are between the two different elements. And in this part, I'll tell you about photo association resonances as well as Feshbach resonances between these two species. And in the third part, which is more recent work, it's actually not yet published. I'll tell you about some experiments on many-body dynamical delocalization, in which we see the spread of an atomic distribution, in this case in momentum space, driven by interactions. Okay, so just to very quickly set the scale, I know you've been hearing a lot of talks about cold atoms and cold ions and cold molecules and so on. Very quickly, let me just put the key energy and temperature and length scales in context. It's the coldest really that we can make things in the lab. Most of the interactions we have going on are S wave because the temperatures are below the P wave threshold of a millikelvin or so, where the de Broglie wavelength is on the scale of few nanometers at that point. And then in the quantum degenerate regime, you're at the few hundred nanometer de Broglie wavelength, where this length scale becomes on the order of the interparticle spacing. And at this point, you're at a microkelvin. Typically, experiments are in that regime or even below. And the confinement is in traps, where the ground state oscillator energy maybe is a few nanokelvins or so. And this gap in energy from what we're normally encountering to these ultra-low temperatures is through the sequence of laser and evaporative cooling. And typical samples that we will end up with as routine in most labs working on these sorts of experiments, maybe 100,000 particles at maybe 100 nanokelvin with densities of 10 to the 14 per cubic centimeter. These are the neutral atom systems. And this very low level of energy, good control over quantum states, and interactions being controllable and not that huge, mostly two-body, makes it a great starting point for studies and various studies in quantum physics, and can study old ones, create new systems, great platform for quantum simulation, quantum information processing, and also new kinds of precision measurements. And you've been hearing many of these through the school and the conference. So in our case, we have one atom from the alkali column, lithium, and another one from the group 2. It has the electronic structure of a group 2 atom. It's deuterium over here. It's a 2-electron atom, and importantly, it's not an alkali atom, a closed shell atom. The other ones that are colored are, to my knowledge, the ones that have been brought to quantum degeneracy in different labs. Our apparatus looks something like this on the length scales of a regular optical table, with the two species being fed into a common vacuum chamber through two different atomic beam setups. Lithium here is shown in red, ytterbium in blue. Here's a photo of a part of our laser system, It's kind of visual because lithium's strong transition is at red, 671 nanometers. Actually, we saw a picture of this earlier in Salik's talk. And ytterbium, the magneto-optic trapping is at 556 nanometers, which is nice and green. So here's a sequence of photographs taken as the two species are combined in a co-located magneto-optic traps, after which they proceed, or they are coaxed into an optical dipole trap. In our case, optical dipole trap wavelength is about 1 micrometers. And because the AC Stark shift is different for the two species at that wavelength, it's about a factor of 2 different. And because the masses are quite different, the trapping frequencies end up being a factor of 8 or so apart. And the sequence in which we do our cooling is we cool the ytterbium in a regular evaporative cooling way, and the lithium gets sympathetically cooled. We do a few adaptations of regular evaporative cooling called painting, in which we increase the size of the optical dipole trap in a controlled way. But those details, if you're interested, can be found in this paper here. So once things are working well, the combined system can produce quantum degenerate gases of either bosons or fermions, or a combination. In this case, there's a coexistence of a quantum degenerate Bose gas of ytterbium. You have a Bose-Einstein condensate. And here is the degenerate Fermi gas of lithium. And what these dashes show, this dash line here shows attempt at a Maxwell-Boltzmann distribution fit, which fails, and one has to do a Fermi-Dirac distribution fit in order to get the correct temperature. So on top of cooling the particles down to these quantum degenerate temperatures, one can look at how to control their interactions. And that's a key enabling element for many atomic physics applications today. And one standard one, I guess I should say, is the so-called Feshbach resonance, in which you have the a degeneracy between a pair of free atoms and the bound state of those same atoms. And you tune the degeneracy condition, or you tune the energy splitting between these two states by an external magnetic field. And earlier today, there was a talk by Professor Rudy Grimm, in which these Feshbach resonances were discussed and applied. So this is how, this is what happens when the magnetic field is tuned. And in the case of the lithium system, there are two entering lithium atoms in the so-called triplet configuration comes into resonance with a bound state in the singlet configuration. And they have different magnetic moments, so you can tune the energy difference between these and have access to a range of S-wave scattering lengths. So this is a very well-used Feshbach resonance in the field. This magnetic Feshbach resonance of 6-lithium between the two hyperfine ground states of 6-lithium occurs at around 830 Gauss. And around this point, the scattering length, S-wave scattering length, can be expressed in this fashion. This is a way to get very strong interactions between fermions, and there's a natural connection now to strongly interacting fermions from other parts of physics, from other walks of life, if you will. So this system has often been called the hydrogen atom of many-body physics, or the harmonic oscillator of many-body physics. it has implications for thinking about the fermions in neutron stars, as well as the fermions, which are the electrons that pair up to form Cooper pairs, superconductors. So that's wide-ranging applications. In our experiment, we can make this by cooling the system at this close to the peak of the magnetic Feshbach resonance. And in order to see that we have created the superfluid state, the paired state, we can move the system to a place where you have more deeply bound molecules, and observe then the condensation of these molecules. So in this case, from our observations of this condensation of these paired lithium atoms, we can deduce that the Fermi superfluid exists at about half of its critical temperature. So that first part that I was alluding to earlier comes into context when you think about what the more traditional superfluids from condensed matter, which have been around for a lot longer, the helium the helium systems, liquid helium systems, 4 helium and 3 helium, even though they're independently brought to superfluidity, when you try to bring them to superfluidity together, you get impeded by the strong Bose-Fermi repulsions. And even though experiments are continuing till today, it's not been possible. So atomic systems, given their lower density and interaction control possibilities, offers an opportunity to create new kinds of quantum systems, even paradigm quantum systems that you couldn't otherwise. So this is our demonstration of this, where ytterbium Bose-Einstein condensate and lithium paired superfluid coexist. This was from a few years back, and this was the first with different elements simultaneous with another group in China who worked on it with potassium and lithium. And there was an early realization in a 2-isotope system in Christophe Salomon's group in Paris. Now, after making the system, we looked at some collective dynamics in the system, and one straightforward way to look at the interactions, how these superfluids play with each other, we excited dipole oscillations in one of them. So we excited dipole oscillations in the ytterbium gas by displacing its center, and then adiabatically displacing its center, and then quickly moving the center back, and it starts to move up and down. And this is the what you see here is us recording how it's oscillating and therefore measuring its frequency. And if you do this with and without the presence of the other element, the other superfluid, then you can look at the difference between these two oscillations. And you can see from here that even though they started basically at the same phase of oscillation, by the time they're here, they've gone out of phase. And from this, you can extract a frequency shift between them. And from that, because you also know the original trap things are in, you can back out then how the two species are interacting with each other. And our shot of this was that the frequency shift was consistent with the mean field model of the system, and the interaction was repulsive. So the in the presence of the lithium, the ytterbium would oscillate a little bit slower because it was being repelled, and the effective trap became a bit weaker. Okay, so another thing we looked at with this combined system was exchange of angular momentum between the two. And we looked at this by
Professor Gupta, there is a question here. Who would like to
yeah,
take?
go ahead.
Yeah, Saikat, can you unmute and ask?
Yeah, it's regarding that gap of data in the middle. Is it from like different shots and different realizations, or is it a single shot?
Okay. Thanks for that question. Yeah, each is a different shot. Each is, in fact, an average of 3 different shots in which the system is prepared. The experiment is done by setting up the system, exciting the oscillation, and waiting for a particular period of time, and then stopping the experiment, taking the image of the experiment of the atoms. And for the next iteration, you have to do it all over again after changing the hold time. And so
how is the phase maintained?
Sorry, what's that?
How is the phase maintained for the oscillations then? Like if it's
because you start it identically each time.
Okay.
You start,
So the preparation is very identical.
Yeah. The atom number may be a little bit different, but how the potential is shifted slowly at first and then very quickly. That timing is spot on each time.
Okay. Right.
Thanks. Yeah.
Okay. I'll proceed.
Yeah.
So here, because the traps for the 2 species are not actually exactly concentric, or don't exactly share the same center. So I'm sorry, I may not be able to see the chat each time. So if there's a question, please feel free to stop and speak up. Because the center is not identical, the movement of this dipole oscillation of one of the gases generates a torque. Okay. So that torque can provide angular momentum, therefore. And what we observed was a particular excitation of a superfluid which contains angular momentum, oscillating angular momentum, called a scissors mode. And there the non-isotropic system undergoes oscillations which can look like this. So the angle with respect to some axis oscillates in time. So in the absence of the second superfluid, we didn't see this, while in the presence of it, we did indeed see this, and this is studied at a couple of different interaction strengths. And here are some Fourier transforms of the data. The frequency of these oscillations is consistent with what one would expect from this sort of excitation. Okay, so I'm going to switch over to the second part of the talk, in which I'm going to talk about interactions between lithium and ytterbium, or tuning interactions between lithium and ytterbium. So it's in the context of diatomic molecules. We just heard Tanya Zelevinsky give a really great talk on molecules, and I'm going to use the motivations were already presented to you a little while earlier, but let me, for completeness, add a few more things. We get new degrees of freedom with molecules, so the scientific reach possible with cold atoms can be enhanced some more. But of course, it comes with technical challenges as well. It's a lot easier to cool directly atoms than it is to cool molecules. So the tack a lot of people take is to individually cool the atoms in the same trap and then try to combine them together. And the kinds of new things that are possible comes with these new degrees of freedom. For instance, an electric dipole moment can give rise to long-range interactions, which are lacking in most just atomic systems. The ytterbium lithium molecule has a relatively modest ground state dipole moment, but it has a reasonably high high one in certain excited states. And importantly, it would be a new class of ultracold molecules. So the ones that have been brought to ground states. So there's the homonuclear ones that Tanya spoke about, strontium 2. Amongst the heteronuclear ones, which would possess these electric dipole moments, the ones that have been brought to ground states and tamed to the ground state are the bialkali ones, where the true ground state actually doesn't have a magnetic moment. So the new thing that such a system like this could bring is then this extra degree of freedom from the unpaired electron. I recall lithium was the alkali, ytterbium is a closed shell atom. So the new possibilities that can emerge now are from paramagnetic polar molecules. They would be magnetically trappable. The molecules themselves, two individual molecules could have Feshbach resonances. You could study chemical reactions which are now spin controlled. And this extra degree of freedom is at the heart of several proposals for enhanced quantum simulation or quantum information processing schemes, and some references over here. These, to my knowledge, are the bialkali systems that have been brought to the ground state thus far.
Professor Gupta, there's a question here in the chat box. Would you like to see it?
Yeah.
Otherwise, I can ask. Sourav, could you unmute and please ask the question?
Okay. Hi. So this dipole moment, has this been measured? Because I recall that there was some discrepancy between some calculations of Olivier Derive and very early on, I think the Andrei Derivienko, that somebody said that there is a dipole moment, there isn't a dipole moment. So has it been measured, is the thing?
It has not been measured, but you're right, there's many calculations. I know of like 4 or 5 calculations of this, and I think even Bhanu Das might have been involved in one of them as well. And I don't think there's an agreement, so measurement would be great, but we're not there yet.
Nice. Yeah, very nice. Yeah, good. Okay. Okay, thanks.
So, Sadiq, you have a question?
Deep, just question. See, this is often said that, the magnetic moment is going to be in a different direction from the electric dipole moment. But I mean, isn't there this thing of a vector operators all collapsing on the same axis because of Wigner-Eckart? So, I'm not so sure whether the magnetic moment is an independent, degree of freedom in terms of at least the angle.
I see. Okay, that's quite. I'm not sure I can fully respond to that, but it is another degree of freedom, and the proposals that I've seen rely on the new term in the Hamiltonian, which coming from the spin rotation coupling. So so it does introduce a new term in the Hamiltonian, which can then be applied to do something useful.
I will torture you on this question later.
Okay. All right. Looking forward to that. Okay.
Thanks. Yeah, right. Just go ahead.
Yeah. Okay. So as several of you know, I think the way in which this battle is fought is to first combine the atoms into a weakly bound molecule, and then do some 2-photon Raman process to get to some targeted final state. And what I'll tell you about is some photo association work in which we identified the various bound states, and then using the locations of these bound states, we were able to deduce where the Feshbach resonances would be, and then went and observed and studied those Feshbach resonances. So this is a quick reminder of that Feshbach resonance action. Now, importantly, and this has been, I'm putting it in one slide, but this is a lot of work to approach experimentally. For bialkali collisions, you have hyperfine. Well, you have spin from both partners, and so you have terms that have I1.S1 and I2.S2 terms in there, and you have singlet and triplet potentials, which can then get coupled. When you have one closed shell atom and one open shell atom, that's not the case, and we have to rely on a much weaker interaction via the nuclear spin of the closed shell atom and the electron spin of the open shell atom. So this was originally proposed as a coupling mechanism by Jeremy Hudson several years back, but it's taken a while to actually realize this. So I'll be that's where I'm moving towards. Ytterbium lithium, as far as I know, the spectrum was not known until we started looking at it, and how we look at it was the traditional photo association spectroscopy method, which is used in several labs, in which you just shine a laser beam at a wavelength which is a little low, a frequency a little bit lower than the bare atom optical resonance, and you tune it around until you start seeing some losses, and you identify those losses with molecular bound states in the excited channel. And here's one sample spectrum thereof. And you can track this down through the various bound state levels by tuning our frequency and looking for losses. And you're helped a little bit, it's a little bit needle in a haystack, but you're helped a little bit by this formula, the Leroy-Bernstein formula, appropriate for 1/r⁶ potentials. And you can do this now in the ground state as well. An excited state potential, excited state, a particular excited state with one of your laser beams, and you tune a second one to address bound states in the ground potential. And we went ahead and did that and found several of them. And in order to coherently, in order to show some coherence between atoms and molecules, we employed an EIT type scheme, which also we heard about earlier, in which you think about a three-state system in which the two ground states are the two free atoms and two atom bound state, and the excited state forming the lambda is an excited molecule. And if your lasers are locked, then one of the you can probe one of the states of this three-level system, which is a dark state superposition of two ground states here. And indeed, we did see that this hole in the spectrum when you tune when you tune the frequency of the up leg laser, the laser connecting to one of the excited state. So you can use this to identify very sharply what the binding energy is. So on one side, this tells us there's coexistence of ytterbium lithium molecules in the electronic ground state with these atoms. It's a very small fraction that's coexisting, but still it's nonetheless there because we see this signal. Additionally, this tells us exactly or very precisely where the bound state is. And we use this to identify the first bound state in the ground potential, which is the one that's that generates the magnetic Feshbach resonance that I'll get into now. So this is written up over here, and our theory collaborator for this is Svetlana Korjigova at Temple University. This is just showing how that resonance moves with magnetic field, telling us that indeed the the molecule has magnetic moment, which of course we knew. Okay, so I'm going to move into this magnetic fetchback resonance part now. All the spectroscopy that we had done really helped us identify very precisely where this first bound state is. So the blue is the hyperfine structure of the atomic states. So ytterbium has no unpaired electron, so the real hyperfine structure really comes from the lithium atom, at least all the strong stuff here. And you see a similar structure for the first bound state of ytterbium lithium, so the first one below threshold. And these have different magnetic moments and intersect over here, and you zoom in over here, you get this sort of picture. You get these three crossings. You zoom in on any one of these crossings, you get this structure here. So this one down here is the zoom in of the middle triangle. And you get this extra spread because of the nuclear spin associated with the ytterbium here. And I didn't stress this, but the isotope that we're using in this experiment is ytterbium-173, which has a nuclear spin of 5 halves. So there's 6 nuclear spin projections. This is the form of coupling that I had mentioned earlier. S of lithium dotted with I of ytterbium. And if you look at this, you can, I think, see that MS plus MI will be conserved.
Prof. Gupta, there is a question here. Yeah?
Yeah, go ahead.
Yeah. Sourav, could you please ask?
Again, Sourav here. So in your previous slide, you showed this loss data where you said that there is a dark state. But you see, I could say that there is a AC Stark-Shift or Ortler-Towns kind of effect between the two bound molecular states, and when you tune your PA laser, you basically measure that. I mean, so it does it really prove that there is a coherence between atom and molecule?
Oh, okay. I see. Yeah. When you go measure this width of this thing, I didn't stress it, but it's a lot less than the natural line width of the excited state 6 lithium here. So I think that would then suggest that, yeah. So we got it down to like 100 kilohertz or maybe a bit less, and that's and the excited state line width of lithium is 6 megahertz.
Right, but you were splitting Ortler-Towns splitting could be less than the line width, as far as I understand. Isn't that true? I don't know. Okay, let's move on.
In that case, maybe we're talking about the same thing here, because we may be talking about the same thing. And probably the Ortler-Towns converts into this picture that you have this dark state in which the coherence, the excitation from the 2 paths that could take you up there destructively interfere.
Okay, fine. Thanks.
Sure. Oops. Okay. So, right, if you look at the form of this interaction here, I think you can convince yourself that the M sub S and M sub I, the sum of that will be preserved, will be conserved, because you have an S dot I kind of interaction. And that's the reason why, because in these resonances, the MS changes by 1, because the lithium goes from, in the atomic state, it's in -half, and the molecular state, it's +half. And therefore, the MI also has to change by 1 in the other direction. And that's why there's one resonance missing here. Like there's going to be 5 resonances, because MI has to change by 1. So we go looking for these things. Now that we had a very precise number for where that bound state is, these resonances are actually very, 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 very sharp. So if we didn't have a good idea of where they were, it would be very hard to go looking for them. So indeed, we do find these resonances here measured in number loss. at the predicted values. And I mention here that these sorts of resonances were observed by Florian Schreck's group in strontium rubidium, which has a very similar electronic structure, in 2018. And in our work, we observed it in ytterbium lithium collisions, and we also went ahead and studied the magnetic substructure as well as the temperature dependencies, which is what I'll get into now. More recently, I know that it's also been seen in cesium, ytterbium cesium in Simon Cornish's group, but I don't think there's a publication yet on it. Right, so those 5 resonances that I was mentioning with one missing do indeed show up in our work, where we have to purify the spin state of ytterbium and then put that in combination with the lithium atoms. And as the magnetic field is changed, depending on which spin state is used, there's a different location of the resonance that we find. And in one of the spin states, there is no resonance. So this checks out. And we look at this shift, and in combination with theoretical work from Aita Tisinga and Svetlana Korchugova, we see that indeed it does follow what you would expect, this size of the shift. We also looked at the temperature dependence of these resonances, and here are for 4 different sample temperatures. And one obvious thing is that things get broader as you get hotter. And the other thing is you see a shift in the resonance location with temperature. And our theoretical collaborators built a model about this as well. And the sort of the quick take is that it first of all has to shift to the right, and that's or to higher magnetic fields, and that's because, let me just scroll back here, if the kinetic energy is higher, then the resonances will occur at or the crossings will occur at a slightly higher value of the magnetic field. Okay. Just the way the kinetic energy always has to be positive energy shift for the atoms, so all the blue lines will be slightly moved up. That checks out. And then kinetic energy means there's a broadening of the initial energy distribution, and therefore you can imagine that there's a larger range of fields at which you would see a resonant effect, and the physical process that's happening is a 3-body loss, which is why you see these you see atom loss, and so this 3-body loss maximum moves to higher fields, and the line width gets broader. How much it moves depends on the relative magnetic moments, and the rate, the actual height of these peaks, then can also be modeled. And what our theory collaborators found was that it does obey the rate that you would get for collisions between 2 fermions, collision between 3 fermions, only one of which is non-identical. I mentioned here that this is also a strongly interacting Fermi-Fermi system, which is mass mismatched. Here it's by a factor of 29. It's a very large mass mismatch. And I know earlier today there was a talk by Rudy Grimm on mass mismatched Fermi-Fermi systems. So I want to point out this connection here. So, we have these magnetic Feshbach resonances. They're very narrow because of this weak coupling that I was discussing. However, we think that it should still be possible to coherently associate into molecules, and this is the standard picture for thinking about this. As you sweep magnetic field, you can adiabatically move from 2 bare atom states to a molecule state, and these are symbols for the associated Rabi frequencies. Here's the relative magnetic moment. However, you're going to be fighting with other processes which which can disturb this. Because the line width is so narrow, we need to put it into an optical lattice to protect the atoms. And this is underway right now. We've actually set up our 3D lattice, and here's some sample images from it. Here's diffraction from a 2-dimensional lattice. Here's a Mott insulator transition of the bosons in a 3D lattice. And I'm gonna, hopefully I have a few minutes to talk about the last part of my talk.
Yeah, probably 2 minutes. Yeah.
2 minutes, okay.
Okay.
Yeah, I'll do it quickly. I'll do it quickly. So this is very, very recent stuff, which we're pretty excited about in an optical lattice. And I'll just get straight to it. This is the Hamiltonian under consideration. It's a quantum kicked rotor Hamiltonian, where you have kinetic energy and a pulsed kick, which in the form of delta function, which you would realize by some kind of AC Stark shift in a quantum mechanical problem. And I draw your attention to the classical kicked rotor, which is a textbook example of chaos in classical mechanics. And this connection between the classical model and quantum chaos has been a strong subject of investigation for decades now. And the first atom optics realization of this of Hamiltonian was by Mark Raisin, followed by several others, in which these kicks were applied by flashes of an optical lattice, providing essentially what's called a Kapitza-Dirac diffraction pulses, repeating one after the other. And this quantum mechanical model of this kicked rotor has been shown to be equivalent to Anderson, an aspect of Anderson localization. So this model, this Hamiltonian, exhibits dynamical localization in momentum space. So if you keep kicking the system, the momentum doesn't increase without bound, it saturates, and which is equivalent to a localization behavior in momentum space is linked to Anderson localization in position space. The classical model, on the other hand, the energy increases basically linearly in time for characteristic of a diffusion process. So this work, we acknowledge great discussions with our collaborator, David Weld, UC Santa Barbara, who's doing these sorts of experiments by turning on Feshbach resonance. And in our case, we are using higher densities to look at this effect. Also acknowledge theory collaborator Chuan-Wei Zhang at UT Dallas. There's a large body of theoretical work on quantum kicked rotors where this localization behavior is supposed to be destroyed, but there were no prior experimental signatures. So now I'll just go straight to our observation of this in a low density situation. What these are different momentum states that are excited under the action of this rotor, under the action of these standing waves. So in a low density situation in a regular 3D trap with low scattering length, some numbers here, we see that the momentum doesn't really change after a while. So the 40 pulses are applied here. Whilst in a higher density situation, which we achieve in a 2D lattice arrangement, the momentum starts to grow. And if you now plot the energy versus time, in this low density case, you see the saturation. In the higher density case, you see this growth. And this growth, you can, in this log plot, you can model and see that it obeys some kind of power law with the exponent, which is actually less than 1, indicating it's sub-diffusive. We've done some other characterizations of it versus different kick strengths and also reduced density and so on. And here's the upshot of this thing that we're observing: delocalization momentum space, 1D tubes. Can be a platform for many-body localization, delocalization studies. Energy growth measured to be sub-diffusive, consistent with some early theoretical models, and some more complete theoretical modeling is underway with our collaborator. All right, so I won't belabor this anymore. These are the things I've been telling you about, and I really want to thank the group that's been doing all of the work. This photograph was, of course, taken before the pandemic. And thanks very much, everyone. You can take more questions.
Yeah, thanks. Are there any questions from the audience?
I have a question. So it's a very nice talk. So regarding the first part of your talk, so you have shown the phase shift in breathing mode. So is this phase shift related to the collisional phase shift, inter-species collisional phase shift, or is it related to some superfluid hydrodynamics?
Okay, thanks, Bimalendu, and good to see you again. This is can be entirely modeled by looking at the Fermi distribution density and treating it as a mean field term. And so the density times some effective interspecies scattering length. It can be explained by that, just using that.
The both species are in superfluid regime.
Yes.
They're
yes. So these shifts, the value of the shift can be changed by looking at different magnetic fields where the interaction in the Fermi superfluid is different. So the size of the Fermi superfluid is different, and therefore the density distribution is different, and that changes the value of the frequency shift.
okay. Thank you.
Sure.
Any further questions?
Since no one is asking, can you detect these molecules in the lithium terbium thing in your apparatus somehow? Like that would tell you that you really have a dark state, right?
Can I detect the molecules? That the fraction, if you look at the shape and you calculate how much you expect in there, it's actually a very small fraction. It's maybe 10 to the minus 3 or 10 to the minus 4, something like that. So we of course tried it, but it's such a small fraction, we didn't really expect to see it directly.
Okay.
It's getting late over
here. Sorry, yeah, it's yeah. So
I understand.
Thank you, and yeah, let's all give him a big hand.
Thank you very much. All right.
Thank you.
Thank you.
Okay. Bye. Good night.
Bye.
Bye bye. Good.
Have a nice day. Yeah. Bye. Great. See you, everyone. Yeah. Bye.
Naveen?